Hello everyone. In the last lecture we started talking about ARIMA models. We talked about autoregressive differencing and autocorrelation. So today we are going to continue what we started with. We talked about stationary and how to know whether the data is stationary or no, and some signs that shows that the data is stationary. Also, we talked about the autocorrelation, which is the correlation between the values of the time series in the neighboring period. Also, we give some tips of how to capture the stationary using charts. Also, we are going, by the way, to show or to give some statistical methods today, or in the example, how to know whether the data is autocorrelated or no, or if there is an autocorrelation, or if the data is actually stationary or no. Also, we talked about how to test whether the time series is a random walk by checking at least two of the methods. There is more than two methods, and we are going to mention another statistical method when we do the example. After that, we said that, okay, after modeling the trend and seasonality, residuals may still have some autocorrelation. So we can do the modeling, or we can do the forecasting using two methods. The first one is using the two-layer approach. In this case, we develop just the first model that handles the trend and seasonality, whether this one's going to be linear regression or it's going to be ETS, whatever, or halt winter. It depends on your data. After that, we use a second layer, which is AR model, autoregressive model, and this happens on the residuals, and we've seen in the example of ridership. The second approach that we're going to do today is going to do using the whole model once at one, as ARIMA model. Okay, it's preferred to use the first method, two-layer approach, because the other one is automated, and we are going to see this and speak about this during the example. So the second approach is we create a large set of flexible models. It is large set. ARIMA stands for Autoregressive Integrated Moving Average Model. AR autoregressive, I integrated, MA moving average. And this automated model directly models the autocorrelation of the series as well as the autocorrelations of the residuals. And we can look at the equation, the first equation, which is the autocorrelation part. This is the autocorrelation at lags 1. And we are familiar with this. The second part that we added to this is the moving average part. And these thetas are similar to betas. So these thetas are similar to beta. There's something extra here, which is epsilon t. So I have to remove this off. So we have theta 1 times epsilon t minus 1, theta 2. These are parameters like betas. We need to estimate them. So this is the second part that we added to the estimation equation. So in this case, we estimate or predict y. And as we mentioned, AR and ARMA can be fitted to data without trend or seasonality. That's why we add the I, which is the differencing in this case. Differencing is to allow the model deal with trend and seasonality. So ARIMA, the whole model, the automated one, can deal with the whole process, the whole thing, the whole data set, the whole time series. There's no need to do anything else. We can just play with these parameters and change them to handle the trend and seasonality, and look at the residuals as well, the autocorrelations if exist. So as we said, ARIMA models add the step of differencing. So the step of differencing is added to ARIMA, not as we said, ARMA. It doesn't. And they are integrated in the ARIMA. And the order of differencing, we call it D, and that indicates how many rounds of lag 1 differencing are performed. If D is 0, that means we have no differencing, which is suitable if the series lacks a trend. D equals 1, that means we are differencing once at lag 1. So that means you see a trend and linear trend, and you try to do a differencing here at lag 1. If you see D equals 2, if you put D equals 2, that means differencing the series twice every time at lag 1. That removes the quadratic trend and so on. And we have seasonal ARIMA, some books they call it ARIMA. Seasonal ARIMA model that gets a step of differencing to remove seasonality or the autocorrelation terms for capturing the remaining seasonal effect. So we do have a seasonal ARIMA, and the D number it's a different D, different in different place. We can add how many times I would like to do differencing for the seasonality. So far we talked about how linear regression models can capture trend and seasonality and autocorrelation through the autoregressive models. Also, there is something that we need to know. Regression models can also capture additional type of patterns that are common in real-time series. These things are outliers. This can be captured, as you've seen in this graph. Special events. Maybe there's a special event, or this is outlier, we don't know. Interventions and policy changes, maybe something happened here. And maybe correlations with other series. And we are going to talk about every individual of these just quickly. The outliers, we know what the outliers are. The outliers are the extreme data values. As in cross-sectional linear regression, a fitted regression model can be affected by outliers. So, if the training period contains one or more outliers, it's important to carefully assess their effect on the estimated model. To do that, we can fit the model with and without the outliers and see how much the predictive performance is affected. If dropping the outliers does not have much effect, then we can fit the model with the outliers. If the outliers do affect the model, then we should consider removing their effect. We can simply remove these periods from the training data and fit a regression model without them. While the regression models can be fitted to series with missing periods, smoothing methods cannot be applied with missing data. And this is important. We have to have a complete data set. So in this case, what we do, we might consider replacing the outliers with forecasts or imputed values. Using what? For example, you can use the centered moving average. You can take the average and place the value. Another method to removing outliers from the training set is labeling them as outliers and incorporating them into the regression model. So we label them and we incorporate them as a new predictor. So this can be done, as I said, is using a dummy variable that takes the value 1 for periods with outliers and 0 otherwise, and including it as an additional predictor in the regression model. So we deal them as another variable. The other thing that we want to look at is the special events. In some cases, the values in a series are expected to be extreme because of having an unexpected event, unlike the regular patterns like weekends or weekdays. But sometimes we have special events have a known schedule but are less regular than seasonal patterns and are typically shorter. So we're not unlike the weekends and weekdays. These have known schedule, less regular than seasonal patterns, and they're typically shorter, like Christmas Day, for example, Thanksgiving Day. So, like holidays. So, these are the special events like holidays that affects the series, such as, let's say, customers' arrivals and sales. So, if you look at the data set, you see that we have a special events here. There's something happening here, 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 and there, and so on. It's like, and this is impacting the sales. This Look at this example. Actually, it's barbecue sauce. You can tell that, oh, there are special events. People grill more. Look at here. Look at this date here. Like Christmas time, maybe. Here we have July. We're talking about here is July. Here is the Easter probably or something. So this affects the sales or whatever the arrivals. Uh, the holidays can pose a challenge, especially when considering more than a single calendar. Another example in the holidays is sporting events or music concerts with the traffic, so accident rate, etc. So all of these events can have an impact on the data that we are looking at. So how to deal with this? As with the outliers, we can choose to remove these periods from the data and model them separately if you have a sufficient instances of some of same event. If you have sufficient data for the same event, you can just model them definitely separately, or you can include them in the regression model again. Special events can be incorporated into the regression model by using a dummy variable, as we did in the outliers. So we just add them as a dummy variable in the model building stage, in the performance evaluation stage, and in the forecasting step as well. So the dummy variable takes two values, either one for the periods with the special events and zero otherwise. During the model building stage, the dummy variable captures special events that took place during the training period and is incorporated as a predictor into the regression model. The same predictor is used to capture special events in the validation period for evaluating predictive power. And finally, this dummy variable is used for forecasting future periods that might include special events. So, this is the way that we deal with these special events. The third thing that could happen is, during our data set, is having some intervention that affects our data. So, in some applications, we know that during the training period of our time series, there was some intervention or policy change that we think might affect the series behavior. For example, a special discount that affects sales, or a power cut that affects electricity use. In such cases, assuming that we know the dates of the intervention, we can either split the series into intervention and non intervention periods and model each period separately. For example, a series during discount season and a series during the non discount season. So we can just have two different things, right? Or else we can use one regression model that uses the information on the intervention period timing and create the same thing. We repeat what we did before. Create a dummy variable that we call it, let's say, intervention, that takes the value of 1 during the periods when the intervention took place and 0 otherwise. So include this intervention variable in the regression model as a predictor. It's exactly as we did in the outlier and the special events. And you can look at the graph here, the gun homicide, that how the number has become lower because of the sentencing law begins in some state or whatever in some place. But look at how the time series or how the data has been affected, and it becomes lower. We have a lower trend now. So these are the things that we have to look at and take into our consideration. And we have so many examples about this, like September 11, the flights number, etc., or the people who are traveling through the flights. And the example that you did also, let's say, restaurants or whatever, the sales and the restaurants during or before COVID and after COVID. So note that if you add the intervention predictor and as a dummy variable, and you assign the value of 1 during periods with the intervention and 0 otherwise, this type of model assumes that the intervention effect is fixed. It increases or decreases the values of the series by a fixed amount, regardless of other components in the regression model, such as trendance or seasonality. So to capture the intervention with a multiplicative effect, we can use the logarithmic of the series as the outcome variable. Same variable or same predictor is used to capture special events in the validation period for evaluating predictive power. And finally, the dummy variable is used for forecasting future periods that might include special events. And we talked about outliers, we talked about special events and interventions. Now we are talking about the correlated external series, and this was mentioned before in one of the chapters about the correlated external series. And we describe the difference between the econometric models, where the inclusion of external information is based on a causal theoretical model. This is in the econometric model. And the forecasting methods that include external information that improves the accuracy of a prediction. So we have two different things. So in the forecasting methods, the external information improves the accuracy of a predictions regardless of whether a causal model is present or no. We don't study the causality here. An example about this: when a show is popular, people tweet about it. Tweets do not cause higher ratings, and ratings do not cause tweets. They move together because both respond to the same popularity. So, Twitter data can predict ratings even though it's not a causal driver. Another example, and this was mentioned before, economists notice that during downturns, sales of small luxury items like lipstick often rise while customers cut bigger expenses. So, lipstick sales do not cause recessions, but they correlate with the consumer sentiment before recessions start. So there is a correlation, but not causal effect, not causal relationship. So they might serve as an early signal for economic stress. So the general approach is to including external series in a regression model is based on two-step process. The first step is remove the trend and seasonality from each of the series if they exist. The series of interest yt and the external series yxt. The result is a series with a new thing, which is because we removed the seasonality and the trend is going to be y star t and x star t that contains no trend, no seasonality. The second step is fit a regression model of y star t with the predictors that are lags of y star t and or x star t. So instead of fitting y star equals beta naught plus beta 1 times x star t, we fit y star equals b naught plus b1 y star t minus 1 plus b2 x star t minus 1 plus the error. And so we use the lags of the previous periods of y star and x star because what happens now often depends on what happened earlier if we are doing the correlated external series. And there are two requirements, by the way, two requirements on what external information to include and how such information is included in the model. One affects the values of the predictors, and the other affects the estimated forecasting model itself. And we're going to speak about this in detail next. So we have two considerations. Consideration one: predictor information must be available at the time of the prediction. So when making a forecast for time t, you can only use data that's already known, either past, which is the lagged one, of the external values like xt minus 1, xt minus 2, etc., or forecast to the future values if they available if the variable itself is predictable. Availability matters not just for timing but also for the data delays. So sometimes even if a variable corresponds to the same period, it's not yet published or available when the forecast is made. So we use lagged or forecasted values. For example, as you see that we have the airfare versus the gas prices. The airfare depends on the fuel costs, so the gas prices can be useful predictors. When forecasting airfare for week T, let's say, we can use the last week's gas price lagged version, like airfare sub T is equal to beta naught plus beta 1 times the gas price T minus 1 plus the epsilon. This is the lagged value T minus 1. Or we can use the forecast gas prices. We can use the forecasted gas prices for the same week. So airfare T sub T equals beta naught plus beta 1 forecasted gas price sub T plus epsilon. So using forecasted predictors requires an additional forecasting model. And remember, because it's a forecasted, so you have to have another model external for the external variable. It's a more complex, but it's more strong or powerful method. The second consideration, the second consideration is data availability at time of a prediction with the time series forecasting. It's important to update the model as new information arrives. Continuous updating requires that we assure that the model is trained only on the data that is available at the time of a prediction. And the training period must take into account data availability and the forecast horizon. For example, forecasting 1 week ahead for the airfare rates requires the forecasting model to be trained only on data that is available up to the time of a prediction. And this depends actually on how quickly we receive prior weekly airfare and gas price figures. Any delay in acquiring the information must be taken into account in choosing the training period. Let's say a delay of 2 weeks requires shifting the training period 2 weeks back, thus requiring 3 steps ahead of forecasts. In other words, even when training data are available right up to the time of predictions, if in practice we will have a 2 week delay in getting data, we must not include the last 2 weeks of the training data in the model, though we can include forecasts of those data from a separate model. So we have to be careful to the choice of the training period is needed here, not only for the predicting or producing the forecasts, but also when evaluating predictive performance. Validation period forecasts should be based on models that were estimated or trained only on the data was available at the time of a prediction. The box office example, it's one of the things that we have here as an external variable. When forecasting the opening weekend box office revenue, the model must only use predictor values that are available before the movie opens. Because tweet rates are observed daily, the only tweet data known at time t are the tweet from previous days, which is the lagged predictors are required here. So that's why the box office revenue sub t, as we are predicting the revenue, is going to be something like that. It's going to be beta naught plus beta 1, tweet rates t minus 1, the lagged values, tr t minus 2, beta 2, beta 3, tr t minus 3, and so on. Plus beta 8, which is we have a number of theaters, sub t, because this is known in advance. So you must use data available before the time at t. And the tweet counts from the last 7 days are known as you see, TRT minus 1, TRT minus 7, it's up to TR minus 7. And tweet counts for day T are not known yet. So we don't know. So we cannot be used this one. We cannot use TR sub T. And the number of theaters already we know it in advance. So it's published. So we can use that one. Again, no causal claim is made. The predictors are chosen because they improve the forecast accuracy, not because the tweet cause revenue. Thank you.